Hence the last section in chapter 11. The sign-in sheet. So we're going to talk about some more terms like mutually exclusive. And then we're going to look at the addition rule for events that are mutually exclusive and the addition rule for probability for the events that are not mutually exclusive. For the first thing we're going to do is define mutually exclusive. Two events are mutually exclusive if they cannot both happen at the same time. Rolling an even number and rolling an odd number on a dice. Those are mutually exclusive events. It's either even or it's odd. It can't be both. But getting a 3 and a heart in cards, that is not mutually exclusive because there is a card that is a 3 of hearts, right? Getting a prime number and getting an even number is not mutually exclusive because 2 is both even and prime. So one of the first things you want to ask yourself when we talk about the addition rule for probability is, can both events happen at the same time? If they can, then the rule you're going to use is a little different than if they can't. Does everyone understand the definition of mutually exclusive?
They cannot happen at the same time.
Yes, they cannot happen. So this indicates that either one or the other must occur, but not both, if they are mutually exclusive. So the first example is just classifying mutually exclusive. So if you look at a standard deck of cards, determine whether the events are mutually exclusive. Drawing a 4 and drawing a 6. Is that mutually exclusive? Is there any cards that are both a 4 and a 6 at the same time? If you're going to draw one card, then it's either a 4 or a 6 or not. Before, it can't be both a 4 and a 6. B, drawing a 4 and a heart. Is that mutually exclusive?
No.
No, it's not mutually exclusive because the 4 of hearts is one card. I can draw a 4 and it end up being a heart at the same time. It is possible for the events to happen at the same time.
Okay, I'm confused. Okay, so mutually exclusive, they can't happen at the same time.
Correct.
Okay.
They're mutually if you
Okay.
think of exclusive, mutually exclusive, meaning they can't both happen at the same time. Mutually exclusive means they both happen at the same time. They have nothing in common. You can kind of think of it that way. Yeah, so drawing a 4 and drawing a 6, this is mutually exclusive. Oops, went all the way back to the beginning.
So that would be yes.
Yes. Drawing a 4 and drawing a heart is not mutually exclusive. Because there is one card that is a 4 of hearts. So both events can happen at the same time. See that? So sometimes the definition or the lingo or the notation kind of gets in the way. Mutually exclusive means they cannot both happen at the same time. If they can happen at the same time, then they're not mutually exclusive. So addition rule for probability. The first thing we're going to look at is the word or. So the probability of A or B happening, if they're mutually exclusive. If they're mutually exclusive, it's simply the probability of A plus the probability of B. Right? If they're mutually exclusive, they have nothing in common. It's the probability of A plus the probability of B. And we'll see this with the word or.
That's if they are in common.
If they are mutually exclusive, they have nothing in common. They can't happen at the same time. Right?
The wording is like
The mutually exclusive meaning they have nothing, they can't happen at the same time. There's no overlap. If you think of back in chapter 2 when we did Venn diagrams, if you think of the cards that are 4s and the cards that are hearts, right? We have the 4 of diamonds, the 4 of clubs, the 4 of spades, but we have a 4 of hearts, so they overlap here. So these are not mutually exclusive because there's something in the middle. There's something that can be in both groups. If they are mutually exclusive, they have nothing in common. They have no overlap. So this example here, a restaurant has 3 pieces of apple pie, 5 pieces of cherry pie, and 4 pieces of pumpkin pie in its dessert case. If the customer selects at random one kind of pie for dessert, find the probability that it will be either cherry or pumpkin. It can't be both cherry and pumpkin because they're only picking one, right? So if I want to know the probability that it's cherry or pumpkin, that's the probability that it's cherry. Oops. Plus the probability it's pumpkin. Because they're mutually exclusive. It's either a cherry pie, a pumpkin pie, or a apple pie. So what's the probability that it's a cherry pie?
4 out of 12.
There's 5 cherry pies.
Yeah.
5 out of 12.
5 out of 12. What's the probability it's pumpkin? 4 out of 12. So 9 out of 12 is the probability it's cherry or pumpkin. You see that there? Mutually exclusive. I think once we get to an example where they're not mutually exclusive, it's going to make sense what we end up doing there. And you can simplify that to 3/4. 3/4 of the pie case is either cherry or pumpkin. A card is drawn from a standard deck. Find the probability of getting an ace or a queen. What's the probability of getting an ace or a queen?
It would be 8 out of 52.
It would be 8 out of 52. And then that would be simplified to 2 out of 13. So along the same lines, ace or queen, they're mutually exclusive. You either get an ace or you get a queen. You can't get the queen of aces. Doesn't make sense. Or the ace of queens. Doesn't make sense. So you can kind of count up the cards. How many aces are there and how many queens are there? 4 aces, 4 queens, add that together. There's 8 that fit the criteria, being an ace or a queen, divided by a total of 52 cards. And then algebraically, that simplifies to 2 over 13. You guys see that? Find the probability the card is either a club, a diamond, or a heart.
39 out of 52.
39 out of 52. There's 13 clubs, 13 hearts, and 13 diamonds. They're all mutually exclusive, so 13 out of 52 plus 13 out of 52 plus 13 out of 52 would be 39 out of 52. You could also take 52 minus 13 to get 39, since there are only 13 spades. And then that simplifies to 3/4. Go ahead.
I don't know cards very well,
Mhm.
so I would sit there and go, there's 10, and then there's face cards, but then I would be like,
So you need to know there's 13 cards in each suit.
remember that.
Yeah.
All right.
Because the face cards are like the queen, king of spades and hearts too.
Is ace a face card?
Yeah.
No.
Not in this book.
Oh,
Ace
no.
is not a face card, just Jack, King, and Queen. So there's 13 cards, and you could go back to that figure that we talked about on cards. There's only certain things that come up, like face cards, clubs, diamonds, hearts, and spades. So no, there's 13 of each. There's a total of 52 cards. There's 4 suits, so if you take 52 divided by 4, you get 13. You can also think of here, these are 3 suits out of 4 total suits. So it's 3 out of 4. Out of the 4 total suits, I want to know what the probability of getting at least, or 3 of them. Getting clubs, diamonds, hearts. Getting clubs, diamonds, hearts plus spades would be 1. It's either club, diamond, heart, or spades. So if you take 1 minus a 4, you get 3 fourths. Or you take 52 over 52 minus 13 over 52, and you get 39 over 52. So there's more than one way to approach this problem. Here, we're kind of emphasizing the or and the probability of club, diamonds, or hearts. They're mutually exclusive, so you can just break it up as probability of clubs plus the probability of diamonds plus the probability of hearts, which each is 13 out of 52. Add that and you get 3 out of 4. Addition rule for events that are 2 events, the probability will occur, are not mutually exclusive. The not mutually exclusive, you have to kind of take out the repeats, right? If it can be an A, it's kind of like the number of elements in A plus the number of elements in B minus the number of elements of the repeats, which are the ones that are in A and in B, right? So if I had an element in A and that same element in B, I counted it twice. So I need to subtract it once because I only want to count it once. And we'll do some examples, and I think it's going to make sense after we do some examples. A single card is drawn from a standard deck of cards. Find the probability that it's a king or a club. What's the probability it's a king or a club? So I could write this out, the probability it's a king or a club. I can think the probability of king plus the probability of club minus the probability of the king of clubs. Right? How many kings are there? 4, right? So this is 4 out of 52. How many clubs are there? How many king of clubs are there? 1. So 16 out of 52? These are not mutually exclusive because you can get a king of clubs. The cards before were mutually exclusive because you couldn't get a 6 and a 4, or you couldn't get an ace and a king.
How did you get 1? Like I got the 4 and the 13.
Mm-hmm.
How did you get the 1 out?
The 1 here, oops, I don't want to do that. The 1 comes from the card that it overlaps. How many cards overlap? So really I've included it twice. I've included it here. When I counted the 4 kings, I counted the king of diamonds, the king of hearts, the king of spades, and the king of clubs. And when I counted the 13 clubs, I counted the king of clubs again, right? So I have to take out the multiple. If I was to draw a diagram, and I have here king, and I hear clubs, I have the ace, 2, 3, 4, 5, 6, 7, 8, 9. Is there a 10?
Yeah.
Jack, king, and queen. And then kings, I have the king of hearts, king of spades, and the king of clubs, and the king of diamonds. Wait, I have diamonds here. Well, you wouldn't have to draw this diagram. I just want to show you. If I count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 out of the 52 cards fit king or club, right? But it's kind of like what we did in chapter 2 when we said how many were in A or B. We would count them, but there are 4 in A and 13 in B. But if I was to take 4 plus 13, I need to subtract how many overlap. So that kind of, if we kind of think back to chapter 2, that's the approach in chapter 2 when we talk about sets. We want to know how many are in the union. We count how many is in A plus how many is in B minus how many is in the intersection. And that's exactly what we're doing here. We don't have to draw out this picture though to see that.
This is much easier to understand though. I don't know why.
Because you can think of an example.
Yeah.
Visually, you can think of the cards. Okay, I have the 4 kings and the 13 clubs, and I'm going to take out the king of clubs, and I end up with 16 over 52.
So why didn't you do that instead of saying all that intersection and
Because set theory, and this is what it was leading to with probability, is the probability of this is the union. This is the union of A and B. It's tied together.
It's cards.
So we end up with 4 out of 13.
Would it not always be 1 over something?
It could be more if you think of a different example. If I talk about rolling dice, if I talk about getting an even number or a number less than 5, or a number less than 5, then how many even numbers there are, plus how many numbers are less than 5, and then minus how many even numbers are less than 5. So it's not always going to be 1. It could be more, depending on the setup of the problem. Most times in cards, it will be 1, but not every example will be 1. 2 dice are rolled. Find the probability of getting doubles or a sum of 6. Right? So this example, we might want to draw our picture.
What is this? Is this the sum table?
This is the 2 dice table. The sum of the 2 dice, yeah. So getting doubles, or getting a sum of 6. If I count my circles, right? I can get my answer because I only count what's circled, even though I circled one of them twice. Doubles mean like 1, 1, 2, 2, 3, 3. So this sum comes from 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. There's 6 ways to get doubles. Plus the 5 ways to get the number 6.
We don't count the middle 6 twice, you're saying.
Exactly. So the probability of doubles or a sum of 6 is 10 out of 36. Which would be 5 out of...
Isn't it 9 out of 3?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Am I jumping ahead because I didn't count the 6 twice?
So you got to count it at least once. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, you want to count it once. Or you can think, what's the probability of getting a double? Plus the probability of getting a sum of 6 minus the probability of getting doubles and the sum of 6. So here getting doubles, 6 out of 36, plus the sum of 6, 5 out of 36, minus 1 out of 36, because this one was circled twice, which would give me 10 out of 36. Now you don't have to go through that every time. You don't have to break it up to plus the probability of doubles plus the probability of sums minus that. If you have a picture like this, you can just count how many things are circled. And then, of course, we go through and get 5 out of 18. So if we just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, as long as I don't count this twice. When they're not mutually exclusive, you have to be careful that you don't count the intersection more than once. So if you can visualize, if you can do that with the cards, you can think, okay, there are 4 kings, and then there's 13 cards that are clubs, but one of those was the king of clubs, so I'm gonna only add 12. That's fine if you do it that way. To get 16 out of 52. So in a hospital, there are 8 nurses and 5 physicians. 7 nurses and 3 physicians are females. If a staff person is selected, find the probability the subject is a nurse or a male. So probability that it's a nurse or a male. So probability it's a nurse plus the probability that it's a male minus the probability that it's a male nurse. So how many?
Can't men be nurses?
Yes.
Gaylord Clocker does.
So what's the probability that it's just a nurse?
8,
Out of?
12.
12? 13. Oops, and I wrote 12. 13. Right? That's the probability. If I just pick it, the probability they're going to be a nurse. Plus, what's the probability they're going to be a male?
5. They're saying 3 are females.
7 nurses and 3 physicians are females. So how many total females?
10.
10. So how many total males would there be?
3.
Plus 3 out of 13 total. Minus how many male nurses are there?
1.
1, right? Because there's 7 nurses that are female, and you know that there's 8 original nurses, so 1 out of 13. So 10 out of 13. So do you guys see that? The probability it's a nurse is how many nurses out of the total. Probability it's male is how many males out of the total, minus how many male nurses are there out of the total. And you get the probability that it's male or nurse. May draw a little picture here of this diagram, and you might be given this diagram, and it says there are 8 total nurses and 5 total physicians. What's the probability that it's a male or a nurse? So you would add the total males plus the total nurses. Oh, sorry. A male or a nurse, and 3 males. Yeah. So you would have 3 plus 8 minus the 1 that overlaps. Right? And that's what we did. 8 plus 3 minus the 1. Right? So you would have the total nurses plus the total males minus the overlap. There's one of them that overlaps. So this number, these numbers can be any number, so it's not always 1. And we'll do some examples of the graphs, where I give you a graph of the information instead of the words. The exact same approach, except it's organized a little differently. Let's go to the homework in 11.7. What do I assign in 11.7? 9 through 25. Oh, I've already highlighted them. The first 10 are just asking if they're mutually exclusive. So any of these are kind of free game for a test. So look at number 3. You roll a dice, you get an even number or you get a number less than 3. Is that mutually exclusive? No, because 2 is even and less than 3. So if you rolled a 2, both events can happen at the same time. 4, roll a die, get a prime number or get an odd number.
No.
They're not mutually exclusive, right? Roll a die and get a number greater than 3 or get a number less than 3. Are those mutually exclusive? What number is greater than 3 and less than 3?
There's nothing in common.
Exactly.
So then that is mutually exclusive.
Yes. So this event would be mutually exclusive. You either get a number less than 3 or you get a number greater than 3. It can't be both. There's no outcome that fits both events. So mutually exclusive. Pick a student in your class. The student has blonde hair or the student has blue eyes. It can have both, so that is not mutually exclusive. Pick a student in your college. The student is a junior or the student is a history major. Not mutually exclusive. Pick any course and it's a calculus course or it's an English course. So mutually exclusive. It's either going to be a calculus course or an English course or not. There's no overlap there.
Is it just the odds or is it?
Odds.
Okay.
It's not every other odd. I think it's just odds.
Okay.
It says every other.
Oh, it does. It does says every other odd. Sorry.
Do you want us to do everyone?
Oh, I just wanted to go over just this idea of mutually exclusive because sometimes students struggle with switching it, what it means. So the more examples you do, I think it starts to kind of click. So they're quick to do. It's either, but yeah, only the ones highlighted are the ones that are due. But I figured you're gonna have to do those anyway, so I might as well. Because any of this is kind of free game. If I want to say, okay, I'm gonna pick a mutually exclusive one for the test, I'm just gonna go grab one of these, right? Because I'm not that creative to write up my own all the time. A voter is Republican or a voter is Democrat. Mutually exclusive. A chef decides to make either Parmesan crusted chicken or bacon wrapped sirloin for the daily special. Yeah. There's only one daily special. It's either A or B. It can't be both. Sometimes I lose the applications. Okay, there's no instructions. Young couple is arguing over what month they want to get married, so they decide to grab a calendar and choose a month at random. What's the probability they get married in April or May? 2 out of 12 or 1 out of 6, right? Because it's either April or it's May. You can't overlap. There's no overlap there, so it's mutually exclusive. So you take what's the probability they get married in April plus the probability they get married in May. There's minus 0 over 12 because there's no overlap there. You can always kind of look at that probability of A plus the probability of B minus the probability of A and B, because if they're mutually exclusive, the probability of A and B is 0.
Right. You can't get married in April and May.
Yeah, you can't. Yeah, both. Either April or May. Pretty straightforward. Science course or math course. Mutually exclusive there. Pretty straightforward. All these have been mutually exclusive so far. While conducting an experiment on perception, a psychologist randomly chooses a subject from 9 adult males, 6 adult females, 7 children. Find the probability the subject is an adult male or a child. No overlapping there, right? Pretty straightforward. And an adult. So either adult female or adult male. So no overlapping. 17. Small college campus, there are 5 English professors, 4 math professors, 2 science professors, 3 psychology professors, and 3 history professors. If a professor is chosen at random, find the probability the professor is, and then you have the 4 different outcomes there. English or psychology, math or science, history, science or math, and English, math, or history professor. They're all mutually exclusive. So you don't have to worry about that. 18 is kind of where we're going to start the, some of the examples are not mutually exclusive. So a 4 or a diamond would be just like what we did in our notes. A club or a diamond, those are mutually exclusive. A jack or a black card. This is an example of one where the intersection is not 1, it's actually 2, right? So this one's a jack or a black card. What's the probability that it's a jack? 4 out of 52. What's the probability that it is a black card? 13 plus 13, right?
13 plus 13.
Minus, what's the probability that it's both a jack and a black card? 2 out of 52. Because there's the jack of spades and the jack of clubs. So it'd be 28 out of 52.
So the 2 out of 52 would be simplified into their.
You could simplify it to 1 out of 26, but since the denominator is all 52, algebraically it's going to be easier to just leave it as 52 and simplify at the end.
So just simplify.
Yeah, simplify at the very end. And this does simplify down. What would it be? 14 out of 26, which would go down to 7/13. So yeah. 19 is an example where they're not mutually exclusive. You have 18 juniors, 10 seniors. 6 of the seniors are female and 12 of the juniors are males. Find the probability that's a junior or a female, a senior or a female, or a junior or a senior. So again, some of those are going to overlap. And some of them are junior or senior, either a junior or a senior. Those are mutually exclusive. You can be a senior and a female. So the probability you're a senior plus the probability you're female minus the number of female seniors. You could do the probability you're a junior plus the probability you're a senior minus the probability you're a junior and a senior, but that's going to be 0. So you can always attempt it as they're not mutually exclusive and then come up with the conclusion at the end that they are mutually exclusive. So you can always kind of say, I always want to think about where they overlap when I'm talking about probability using the word or. 21 is an example of a table one. I guess there are 3 different designers here. Choose an item at random, find the probability that it was purchased from Kenneth Cole or is its a dress. So you could add up all the dresses. You could add up all the dresses plus the Kenneth Cole column. So you wouldn't necessarily have to take 24 plus 18 plus 12 plus 36 divided by the total. It's kind of like that dice one. If you circle what meets the category, all the dresses plus all the Kenneth Coles, I just add up the circles. Mm-hmm. And then divide by the total number of purchases. Purchase from, what is it? These 2 numbers. Oops, Michael. Okay. Those are mutually exclusive. There's no overlap. Mm-hmm. All these say or.
Yeah. We say we can basically and we're adding them. But if it's
And means both at the same time. So it could, you know, say it's a dress and it's from Vera Wang. How many dresses? It's a dress and it's from Vera Wang. So it'd be 12. If it said it's a dress or it's from Vera Wang, you would add 24 plus 18 plus 12 plus 15. Because all the dresses would fit that, plus all the Vera Wang. So or, just like what we did in union and intersection, and is the intersection, or is the union. And the union was always larger than the intersection, or at least equal to it. So the and is always going to be, is the intersection, it's going to be smaller. All right, the and is more elite almost, like it's a dress and it's from Vera Wang. It's a smaller collection than it being a dress or it's Vera Wang. So it's going to be a larger probability with or at least equal to it. We have this survey data. Find the probability the person has no opinion. So you would take 5 plus 7 divided by the total. The person is male or is against harsher penalties. So you would add up all the males plus the people that voted that they are against harsher penalties.
So the yeses.
Yes, so the yeses. So the yeses plus the males. You guys see that? Yeah, I don't know why. I don't know if your book looks a little bit better than my, because this was printed from the internet. Maybe your tables in your book isn't so smushed together. It looks like they're better in your book. They are, yeah. Again, you guys can kind of keep going. All of these are very, very similar. Any of them is free game for the exam. I will collect the every other odds. This is one of them. A show is a quiz, or it's shown on channel 97. The show is a drama or a comedy. The show is shown on 103, or it's a drama. Right. Starting to make sense with the or? You got to add up anyone that fits in that category, and you only add it up once. In 11.8, examples. From 11.8, it can be the same approach, the same kind of tables, but we're going to look for mixing up. Well, these are all conditional. So it's actually from 11.6 where we did and. But on 11.7, they're all kind of this idea of or, but on your exam, I can mix up and or on the same problem, right? So if I said, you know, what's the probability it's a quiz show and it's on 103? It's going to be 1 divided by the total, right? If I say and, or what's the probability it's a quiz show or it's on 103, I can put those in the same type of problem. And the approach is just a little different. So be really careful with the word and the word or, just like you were in chapter 2. So 11.8 is going to be the last section that we cover before our review day on Wednesday. So Monday we'll come back, we'll do 11.8. We'll review on Wednesday. I hope to give you the pre-test. I'll give it to you in class on Monday, so you can take it home, look over it. And then on Wednesday, I'll answer any questions on that, and then I'll also kind of go around and just kind of look at that. And I'll post the answers after class on Wednesday, so you have a chance to look at the pretest and then have a chance to do the pretest on your own, and then also get the feedback from the answers. And then Friday will be the exam, and then we go on spring break. I will see you guys Monday.